Long before Antarctica became a frozen wasteland at the bottom of the world, it was a continent pulsing with life. Lush rainforests where dinosaurs thundered through fern-choked valleys, beaches where giant penguins stalked prey taller than humans, and volcanic landscapes where proto-mammals scrambled through ash and steam. This wasn't Antarctica with ice sheets and research stations. This was a green world, a warm world, a world where palm trees swayed under midnight suns and creatures so bizarre, so experimental, that they seem ripped from fever dreams ruled ecosystems that would vanish forever beneath miles of ice. Antarctica wasn't always Earth's freezer. It was once its evolutionary laboratory, testing designs that would spread across continents and others that would die in place, entombed in stone as the world grew cold. This is the story of Antarctica, before the freeze, before the silence, before everything living either fled or fossilized. This is the chronicle of a lost world that once sprawled across the bottom of the planet, warm and alive, and utterly unlike anything that exists there today. Gondwana's southern anchor. Antarctica wasn't always isolated at the bottom of the world. For hundreds of millions of years, it sat locked in the heart of Gondwana, the southern supercontinent that included South America, Africa, India, Australia, and the Arabian Peninsula. During the Paleozoic and early Mesozoic, Antarctica occupied a central position in this massive landmass, connected by broad land bridges that allowed plants, animals, and entire ecosystems to flow freely between continents. Fossil evidence shows that identical species lived across what are now separate continents, proving these connections were real and long-lasting. Antarctica wasn't a remote outpost. It was a crossroads, a junction where evolutionary experiments from different regions met, mixed, and sometimes produced entirely new forms of life. The continent's position during the Permian placed large portions of it well within temperate and even subtropical latitudes. While its southernmost regions experienced seasonal darkness during polar winters, the climate remained far warmer than today. Thick forests of glossopterid seed ferns covered vast areas, their distinctive tongue-shaped leaves fossilizing in coal deposits that geologists would discover millions of years later. These glossopterids weren't related to modern ferns or flowering plants. They were an extinct lineage that dominated Gondwana's landscapes for tens of millions of years. Their presence across Antarctica, Australia, India, and South America became one of the key pieces of evidence supporting continental drift theory, since no modern plant could have spread seeds across thousands of miles of open ocean. During the Carboniferous and Permian, Antarctica's interior contained extensive swamp systems similar to those found elsewhere in Gondwana. These wetlands supported communities of early amphibians, primitive reptiles, and the first synapsids, the lineage that would eventually give rise to mammals. Fossil finds in the trans-Antarctic mountains revealed temnospondyl amphibians, large creatures with flattened skulls, and bodies built for lurking in shallow water. These animals hunted fish and smaller vertebrates, their fossils showing bite marks and healed injuries that tell stories of violent encounters in ancient swamps. Their bones are found alongside fossilized logs, fern impressions, and trace fossils of burrowing invertebrates, painting a picture of wet, forested lowlands teeming with life. Antarctica's coal deposits tell another crucial part of this story. Thick seams of coal, particularly in the Transantarctic mountains, form from compressed plant material, glossopterid, forests that grew, died, and accumulated in oxygen-poor swamps where decomposition was slow. These coal deposits aren't just energy resources, they're time capsules preserving pollen grains, spores, fossilized wood with growth rings, and even preserved plant cells. Analysis of these growth rings shows seasonal patterns, confirming that Permian Antarctica experienced distinct growing seasons despite its high latitude. Trees grew rapidly during summer months of continuous daylight, then slowed or stopped during dark winters. This pattern, months of light followed by months of darkness, created unique selective pressures that shaped how plants and animals adapted to Antarctic life. The supercontinent configuration also influenced Antarctica's climate in ways that seem counterintuitive today. Gondwana's massive size created continental interior regions far from ocean influences, leading to more extreme seasonal temperature swings than coastal areas experienced. Yet Antarctica's position meant it received moisture from surrounding seas, preventing the extreme aridity that affected interior regions of the northern supercontinent Laurasia. Rivers flowed year-round in many areas, fed by seasonal snowmelt from higher elevations and by rainfall that nourished the glossopterid forests. Fossil river channels, preserved as sandstone deposits cutting through older rock layers, show meandering patterns typical of slow-moving rivers in flat forested terrain, very different from the glacial valleys that dominate Antarctica today. Animal life diversified alongside the plants. Early reptiles called parareptiles, distant relatives of modern turtles, left fossils showing they had adapted to a wide range of ecological niches. Some were small insectivores that hunted among leaf litter. Others grew larger, developing specialized teeth for crushing tough plant material or shearing meat. Their skulls show varying degrees of temporal fenestration, openings in the bone that reduced weight and provided attachment points for stronger jaw muscles. These anatomical details reveal evolutionary experimentation happening in real time, as different lineages tested solutions to the same problems: how to bite harder, see better, hear more sensitively, and move more efficiently. Synapsids, the mammal-like reptiles, were particularly successful in Permian Antarctica. Fossils of dicynodonts, herbivorous synapsids with turtle-like beaks, show they range from rabbit-sized to cow-sized forms. Their beaks were used to crop vegetation, and many species had a pair of tusk-like canines that may have been used in social displays or combat. Dicynodont fossils are found in rocks deposited in river floodplains and forest floors, often in mass accumulations suggesting they lived in herds. Some sites contain dozens of individuals preserved together, possibly killed by flash floods or drought conditions that concentrated animals around shrinking water sources. These mass death assemblages provide snapshots of ancient ecosystems, showing which species lived together and how they interacted. The end-Permian mass extinction hit Antarctica hard, just as it devastated ecosystems worldwide. Volcanic eruptions in Siberia pumped carbon dioxide and sulfur into the atmosphere, triggering rapid climate change. In Antarctica, this manifested as temperature swings, changing precipitation patterns and die-offs of plant communities that had remained stable for millions of years. Glossopterid forests collapsed, swamp systems dried out or became choked with sediment. The complex food webs that depended on these ecosystems unraveled. Fossil records show a dramatic decrease in diversity, layers of rock containing abundant fossils, giving way to nearly barren sediments where only the most resilient organisms left traces. Yet some lineages survived, carrying Antarctic genetics into the Triassic and beyond. Certain dicynodont species made it through the extinction bottleneck, their fossils appearing in earliest Triassic deposits. The fact that these survivors are found in Antarctica as well as other Gondwanan continents confirms the land connections remained intact, even as global ecosystems reorganized. Antarctica became a refugium, a place where survivors regrouped and diversified, eventually seeding the Mesozoic recovery that would transform the continent once again. The stage was set for the age of dinosaurs, and Antarctica would play a starring role. The Triassic recovery. The Triassic brought recovery and reinvention to Antarctica, though the pace was slower than on other continents. In the aftermath of the Permian extinction, ecosystems worldwide were simplified, dominated by disaster taxa, opportunistic species that could colonize devastated landscapes quickly, but lacked the specialization of pre-extinction communities. Antarctica experienced this pattern intensely. Early Triassic deposits contain fossils of Lystrosaurus, a pig-sized dicynodont synapside that became one of the most common land vertebrates on Earth. Lystrosaurus fossils are found on every Gondwanan continent, including Antarctica, where they've been discovered in the Freymail Formation of the Transantarctic Mountains. This widespread distribution shows that Antarctica remained connected to other land masses, and that conditions were suitable for large herbivores to thrive. Lystrosaurus was remarkably well adapted to post-extinction conditions. Its body was stocky and low-slung, with powerful forelimbs that suggest it could dig burrows for shelter during extreme weather. Its skull was specialized for feeding on tough vegetation, with a horny beak and only 2 prominent tusks. Studies of bone microstructure reveal rapid growth rates in juvenile Lystrosaurus, suggesting they reached adult size quickly, an advantage in unstable environments where survival to reproductive age was uncertain. Their fossils often show stress lines in teeth and bones, indicating periods of nutritional deficiency or environmental hardship. Yet they persisted, spreading across vast areas and becoming so abundant that some paleontologists refer to the early Triassic as the age of Lystrosaurus. Plant communities during the early Triassic were dramatically different from Permian forests. Glossopterids were extinct, replaced initially by simpler vegetation dominated by lycophytes, ferns, and early seed ferns. These plants were hardy colonizers, able to grow in disturbed soils and tolerate environmental fluctuations. Fossil assemblages from this period show low diversity, only a handful of plant species dominating landscapes where dozens had flourished before. This ecological simplification persisted for several million years before more complex plant communities began re-emerging. The recovery wasn't linear. Fossil records show multiple setbacks where diversity increased briefly before crashing again, suggesting environmental conditions remained volatile well into the Middle Triassic. By the Middle Triassic, Antarctica was warming significantly as global climate stabilized and carbon dioxide levels remained elevated. The continent had drifted slightly, but still occupied high southern latitudes, experiencing long summer days and winter darkness. Yet the warmth was sufficient to support diverse vegetation, including conifers, cycads, and ginkgos, plant groups that would remain important through the Mesozoic. Fossil wood from this period shows well-developed growth rings, confirming seasonal patterns persisted. But the rings are wider than those in Permian wood, indicating faster growth rates, trees responding to warmer temperatures and higher atmospheric carbon dioxide, which acts as a fertilizer for photosynthesis. Archosaurs, the group that includes crocodiles, dinosaurs, and pterosaurs, began diversifying during the Middle and Late Triassic, and Antarctica played host to early members of this radiation. Fossil fragments of archosauromorphs have been found in Triassic deposits, showing that these reptiles reached Antarctica not long after they appeared elsewhere in Gondwana. These early archosaurs were mostly small to medium-sized predators, filling ecological niches vacated by the synapsides that had dominated Permian ecosystems. Their skulls show features that would become characteristic of later archosaurs. Antorbetal fenestrae that lightened the skull, recurved teeth for gripping prey, and modifications to hip and limb bones that allowed more upright postures. The late Triassic saw the first true dinosaurs appear in Antarctica, though fossil evidence from this period is frustratingly sparse compared to better studied regions like South America and Africa. What fossils exist suggest that dinosaurs colonized Antarctica relatively early, probably arriving via land connections with South America. These early dinosaurs were bipedal predators and herbivores, mostly small-bodied forms that hadn't yet evolved the gigantic sizes that would characterize later periods. Their bones show anatomical features, hollow spaces that reduced weight, specialized hip joints, and digitigrade foot postures that made them more efficient movers than earlier reptiles. These advantages would eventually allow dinosaurs to dominate terrestrial ecosystems worldwide. Therapsids, advanced synapsids closely related to mammals, also persisted in Triassic Antarctica, though they were declining compared to their Permian heyday. Cynodont therapsids, the group that would eventually give rise to true mammals, left fossils showing increasingly mammal-like features. Differentiated teeth, including incisors, canines and molars. Enlarged brain case volumes suggesting improved sensory processing, and skeletal features indicating more efficient breathing and possibly warm-bloodedness. Antarctic cynodonts were generally small, probably nocturnal, and likely filled ecological roles as insectivores and small prey hunters. Their presence in Antarctica shows the mammalian lineage was distributed across Gondwana, setting the stage for the radiation of true mammals that would occur in later periods. Rivers and lakes dotted the Triassic Antarctic landscape, their deposits preserving fossils of aquatic life. Temnospondyle amphibians, survivors from the Permian, continued to thrive in freshwater environments. Fossil skulls show these animals retain their flattened, crocodile-like profiles, with eyes positioned on top of the head for watching prey while mostly submerged. Some Antarctic temnospondyls grew large, over 2 meters long, making them apex predators in rivers and lakes. Their fossils are often found with fish remains, showing their diet included abundant freshwater fish that had themselves diversified during the Triassic recovery. Climate modelling for Triassic Antarctica suggests temperatures were warm enough to prevent permanent ice, even at high latitudes. Summer temperatures may have reached 20 to 25 degrees Celsius, with winter temperatures dropping but remaining above freezing in coastal and low elevation areas. This climate supported vegetation year-round, though growth slowed dramatically during dark winter months. Animals likely employed various strategies to cope with darkness: hibernation, migration to lower latitudes via land bridges, or simply reducing activity while relying on fat reserves accumulated during summer feeding. Evidence for these strategies is indirect: changes in bone growth rates, geographic distributions of fossils, and patterns of tooth wear that suggest seasonal dietary shifts. The late Triassic ended with another mass extinction, though less severe than the end-Permian event. This extinction particularly affected large amphibians and various archosaur groups, opening ecological space for dinosaurs to expand. Antarctica's fossil record from this transition is incomplete, but what exists suggests the continent participated in the same patterns seen globally: decline of non-dinosaurian archosaurs and synapsids, coupled with proliferation of dinosaurian lineages. By the end of the Triassic, Antarctica was primed for the Jurassic, when dinosaurs would truly come to dominate terrestrial ecosystems and the continent would enter perhaps its most biologically productive period. Jurassic forests and early dinosaurs. The Jurassic transformed Antarctica into one of the most productive ecosystems on Earth, despite, or perhaps because of, its extreme polar latitude. As the supercontinent Gondwana began its slow fragmentation, Antarctica remained connected to South America and Australia, allowing free movement of organisms across vast distances. The climate was remarkably warm by modern standards, with atmospheric carbon dioxide levels several times higher than pre-industrial values. This greenhouse world lacked polar ice caps entirely, and Antarctica basked in temperatures that supported extensive forests extending to the South Pole itself. Fossil evidence shows conifers, ferns, cycads and ginkgos forming multi-layered forests where dinosaurs browsed, hunted and nested beneath canopies that never experienced freezing temperatures. The most significant Jurassic fossil site in Antarctica is the Hansen Formation in the Transantarctic Mountains, which has yielded a diverse assemblage of dinosaurs, plants, and other organisms. The most famous discovery from this formation is Glaucalisaurus, a prosauropod dinosaur that represents some of the earliest evidence of dinosaurs living at extreme polar latitudes. Glaucalisaurus was a plant eater about 6 to 7 meters long, with a long neck for reaching vegetation and a relatively small head. Its discovery proved that dinosaurs colonized Antarctica early and adapted successfully to conditions that included months of continuous darkness. The anatomy of Glaucalisaurus shows it was closely related to prosauropods from South America and Africa, confirming Antarctica's role as part of a connected Gondwanan ecosystem. Another significant early Jurassic discovery is Cryolophosaurus, one of the largest predatory dinosaurs known from this period and the first carnivorous dinosaur found in Antarctica. Cryolophosaurus was about 6 to 7 meters long and possessed a distinctive crest on its skull, a thin, forward-projecting plate of bone that may have been used for species recognition or display. Its teeth were blade-like and recurved, perfect for slicing flesh, and its powerful hind limbs indicate it was an active hunter. The presence of a large predator, like Cryolophosaurus, implies a productive ecosystem with sufficient herbivore prey to support apex predators. Cryolophosaurus remains have been found with bones from other dinosaurs and evidence of scavenging, showing that even Antarctica's Jurassic environments featured the complex predator-prey dynamics found elsewhere. Plant fossils from Jurassic Antarctica reveal forests dominated by conifers related to modern Araucaria and Podocarpus, southern hemisphere trees that still exist today in South America, Australia, and New Zealand. These fossil conifers grew to enormous sizes, with trunk diameters exceeding 2 meters in some specimens. Growth ring analysis shows rapid growth during summer months of continuous daylight, followed by slow growth or dormancy during dark winters. This pattern created wood with dramatic ring variations, much more pronounced than trees growing at lower latitudes where seasonal changes are less extreme. The wood also shows anatomical features associated with frost resistance, suggesting that while Antarctica was warmer than today, it still experienced occasional cold snaps where temperatures dropped near freezing. Ferns and fern allies form dense understory layers beneath the conifer canopy. Fossil assemblages show these plants included tree ferns, some growing several meters tall, and smaller ground-covering species. The diversity of fern fossils suggests humid conditions with abundant rainfall and likely frequent fog or mist, keeping moisture levels high even during periods between rainfall. Fossil soils from this period show thick organic layers, indicating that decomposition rates were relatively slow despite warm temperatures. This slow decomposition would have created peat-like accumulations of partially decayed plant material, much like modern temperate rainforests, where organic matter builds up faster than it breaks down. Marine environments surrounding Jurassic Antarctica were equally rich. Fossil marine reptiles, including ichthyosaurs and plesiosaurs, have been found in rocks deposited in shallow seas that bordered the continent. Ichthyosaurs were dolphin-like reptiles superbly adapted for fast swimming, with streamlined bodies, large eyes for hunting in deep or murky water, and powerful tails. Plesiosaurs had longer necks and paddle-like limbs, using different hunting strategies to catch fish and squid in coastal waters. The presence of these marine predators indicates productive ocean ecosystems, likely driven by nutrient upwelling along Antarctica's coast and by river discharge carrying nutrients from the forested interior. The breakup of Gondwana accelerated during the Middle and Late Jurassic, though Antarctica remained connected to other southern continents. Rifting between Africa and South America began opening the South Atlantic Ocean, but Antarctica stayed attached to both South America and Australia. This meant animal and plant populations could still migrate freely, maintaining genetic connections across vast distances. Fossil evidence confirms this connectivity. Many dinosaur groups found in Jurassic deposits of South America also appear in Antarctica, and plant fossils show nearly identical species growing across southern Gondwana. The similarity of these biotas suggests climate and environmental conditions were relatively uniform across the southern hemisphere's high latitudes. Seasonal adaptations were crucial for survival in Jurassic Antarctica. While temperatures remained mild, the months-long darkness of polar winter meant that photosynthesis ceased for extended periods. Herbivorous dinosaurs likely migrated to lower latitudes where seasonal light variations were less extreme, following the land bridges that connected Antarctica to South America. Fossil trackways show evidence of dinosaur movements across vast distances, and the alignment of some trackway sites suggests repeated use of the same migration routes. Predatory dinosaurs may have followed these herbivore migrations, just as modern predators follow migrating prey. Alternatively, some dinosaurs may have stayed year-round, reducing their activity during winter and surviving on fat reserves, or by switching to alternative food sources like carrion or dormant vegetation. The Jurassic period established Antarctica as a vital component of Earth's Mesozoic ecosystems, proving that even at extreme latitudes, life could flourish given sufficient warmth and seasonality of light rather than temperature. The forests that covered Antarctica during this time were as productive as any on Earth, supporting complex food webs from decomposers to apex predators. This world would continue into the Cretaceous, when Antarctica would reach its peak diversity and abundance, a green continent teeming with life, unrecognizable from the frozen desert it would become. Cretaceous rainforests. The Cretaceous saw Antarctica reach its biological zenith, transformed into a lush rainforest ecosystem more productive than the Amazon. The climate was extraordinarily warm, the warmest of the entire Mesozoic, driven by volcanic activity that pumped greenhouse gases into the atmosphere and by ocean circulation patterns that distributed heat efficiently to polar regions. Sea levels rose dramatically, flooding low-lying areas and creating extensive shallow seas that bordered Antarctica's coasts. These warm, nutrient-rich waters supported the explosion of marine life, while simultaneously moderating coastal temperatures through heat exchange. Antarctica's interior, though elevated, was largely free of the ice that dominates today, instead supporting vegetation right up to the highest peaks. Hadrosaurs, the duck-billed dinosaurs, were particularly successful in Cretaceous Antarctica. Multiple species have been identified from fragmentary remains, showing these herbivores diversified into several ecological niches. Hadrosaurs possessed batteries of hundreds of teeth, arranged in dental batteries that worked like grinding mills, perfect for processing tough plant material. Their success in Antarctica suggests vegetation was abundant and varied enough to support specialized herbivores. Some Antarctic hadrosaur fossils show evidence of seasonal growth lines in bones, indicating periods of rapid growth alternating with slower growth, a pattern consistent with migration between summer and winter ranges, or with seasonal changes in food availability. Theropod dinosaurs, the carnivorous lineage that includes modern birds, prowled Cretaceous Antarctic forests as apex predators. While complete skeletons are rare, isolated teeth and bones show that medium to large theropods hunted the herbivorous dinosaurs that dominated the landscape. These predators likely employed ambush tactics, using the dense forest vegetation for cover before launching attacks. The structure of their teeth, serrated edges for slicing through flesh and curved shapes for gripping struggling prey, reveals hunting strategies that remained successful for over 100 million years of dinosaur evolution. The most remarkable aspect of Cretaceous Antarctic paleontology is the plant fossil record. which shows diversity exceeding most Mesozoic sites worldwide. Fossil leaves, flowers, pollen and wood reveal forests containing dozens of plant families, including many groups still present in modern southern hemisphere floras. Araucarian conifers remained important canopy trees, but they now competed with southern beeches, Nothofagus, podocarps, and early flowering plants, angiosperms, that were undergoing explosive radiation during this period. Angiosperm fossils from Antarctica include some of the oldest known examples of flowering plants, suggesting the continent may have been a centre of angiosperm evolution and diversification. Fossil flowers preserved in fine-grained sediments show remarkable detail, including delicate petals, stamens, and pollen still in place. These flowers belong to early angiosperm families that experimented with different pollination strategies. Some were wind-pollinated, producing vast quantities of pollen that shows up in sediment cores as dense layers of fossil pollen grains. Others were insect-pollinated, with flower structures indicating they attracted beetles, flies, and possibly early bees. The co-evolution of flowering plants and insect pollinators was already underway in Cretaceous Antarctica, creating ecological relationships that would reshape global ecosystems. Ferns reached peak diversity during the Cretaceous, with fossil assemblages containing dozens of species ranging from tiny ground-covering forms to tree ferns several meters tall. Some Antarctic fern fossils show adaptations to disturbed habitats, areas where volcanic eruptions, wildfires or flooding created open ground. These pioneer ferns could colonize quickly, their spores dispersing widely on wind and establishing populations before slower-growing plants arrived. Other ferns were forest specialists, growing in the deep shade beneath canopy trees where competition for light was intense. These shade-adapted ferns had larger fronds to maximize light capture and different spore structures optimized for dispersal in still, humid air rather than open wind. The animal life of Cretaceous Antarctica extended well beyond dinosaurs. Mammals were present, though still small and mostly nocturnal. Fossil jaw fragments and teeth show these were advanced mammals, including early marsupials and possibly placental mammals, groups that would later dominate post-dinosaur ecosystems. Their presence in Antarctica confirms that mammals had achieved wide geographic distribution by the late Cretaceous and were already diversifying into different ecological roles. The marsupial lineage, which today survives primarily in Australia and South America, may have originated in Antarctica or dispersed through it between those continents. Marine ecosystems around Antarctica were among the most productive on Earth. The surrounding oceans teemed with fish, marine reptiles, and early sharks. Plesiosaurs evolved into giant forms with necks extending several meters, used for ambushing schools of fish or hunting squid in deeper waters. Mosasaurs, enormous marine lizards related to modern monitor lizards, were apex predators in these seas, some reaching lengths of 15 meters or more. Their fossils show powerful jaws lined with conical teeth, perfect for gripping slippery prey. Some mosasaur fossils contain stomach contents including fish bones and shells from ammonites, extinct cephalopods related to modern nautilus. The abundance of life in Cretaceous Antarctica seems paradoxical given the extreme photoperiod, months of continuous summer sun, followed by months of winter darkness. Yet this pattern may have actually enhanced productivity during growing seasons. Continuous summer sunlight meant photosynthesis could proceed 24 hours per day, potentially producing more plant growth than regions with day-night cycles. Plants adapted to store energy and nutrients during summer for use during dark winter months. Evergreen conifers and southern beeches could maintain their leaves year-round, ready to resume photosynthesis immediately when light returned. Deciduous plants shed leaves before winter darkness, reducing energy costs during non-productive months. Animals employed various strategies to cope with seasonal extremes. Large dinosaurs likely migrated following land bridges to regions with year-round daylight. Their size meant they could travel long distances and carry sufficient fat reserves to fuel migration. Smaller animals may have hibernated, reducing metabolic rates and surviving on stored energy. Some possibly remained active year-round, switching food sources seasonally, eating insects and green vegetation in summer, then carrion, seeds, or dormant invertebrates in winter. Evidence for these strategies is indirect but compelling, including changes in tooth-wear patterns suggesting seasonal dietary shifts and bone histology showing seasonal growth variations. By the late Cretaceous, Antarctica remained biologically connected to South America and Australia, but the fragmentation of Gondwana was progressing. The seaway between Antarctica and Australia began opening, though the connection remained intermittent with possible land bridges persisting during low sea level stands. This gradual separation meant biological exchanges continued but became less frequent, allowing Antarctic species to begin diverging from relatives on other continents. The stage was set for the end Cretaceous catastrophe that would reshape global ecosystems and ultimately set Antarctica on the path toward frozen isolation. The asteroid impact and dinosaur extinction. 66 million years ago, a catastrophe from space ended the Cretaceous period and transformed Earth's biosphere in a geologic instant. An asteroid approximately 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico, releasing energy equivalent to billions of nuclear weapons. The impact excavated a crater nearly 200 kilometers across, vaporizing rock and sending plumes of superheated debris into the upper atmosphere. This debris rained down globally as molten spherules, igniting wildfires that consumed forests on every continent. Antarctica, located on the opposite side of the planet from the impact site, nevertheless experienced the full force of this global catastrophe as shockwaves traveled through the atmosphere and Earth's crust, triggering earthquakes, tsunamis, and environmental devastation that would last for years. The immediate effects in Antarctica would have been terrifying and destructive. Though far from the impact, the continent experienced intense thermal radiation as debris re-entered the atmosphere, heating the air to temperatures that could ignite vegetation. Fossil charcoal layers in the latest Cretaceous deposits show evidence of widespread wildfires, confirming that Antarctica's forest burned during this period. The fires consumed organic material accumulated over millions of years, sending vast amounts of carbon dioxide and smoke into an atmosphere already choked with asteroid debris. Darkness followed as dust and ash blocked sunlight, plunging Earth into an impact winter that lasted months or years. For photosynthetic organisms, this darkness was catastrophic. Plants that had thrived under Antarctica's summer sun withered and died as photosynthesis became impossible. The die-off cascaded through food webs. Herbivores starved as vegetation disappeared. Then carnivores starved as herbivores vanished. Ecosystems collapsed from the bottom up, with only those organisms capable of surviving on detritus, scavenging, or dormancy making it through the initial crisis. Fossil pollen records show dramatic changes across the extinction boundary, with diverse Cretaceous pollen assemblages giving way to low-diversity assemblages dominated by fern spores, evidence that ferns, which colonized disturbed habitats quickly, took over landscapes where complex forests once stood. Dinosaurs, which had dominated terrestrial ecosystems for over 160 million years, faced extinction. The non-avian dinosaurs, the enormous herbivores and their predators, disappeared completely from the fossil record at this boundary. In Antarctica, as elsewhere, dinosaur fossils are abundant in late Cretaceous rocks, but absent from Paleocene deposits above the extinction boundary. The mechanism of their extinction was multifaceted. Immediate deaths from impact effects, starvation during impact winter, ecosystem collapse that eliminated food sources, and possibly longer-term climate disruption that prevented recovery of surviving populations. Yet not all life perished. Birds, dinosaurs that had evolved flight and smaller body sizes, survived the extinction, probably due to their ability to fly long distances in search of food, their relatively low energy requirements compared to giant dinosaurs, and possibly their seed-eating capabilities, since seeds could survive dormant during impact winter. Mammals also survived, benefiting from small size, burrowing behaviours that provided protection, and generalist diets that allowed them to exploit whatever food sources remained. In Antarctica, these survivors would form the core of new ecosystems that were rebuilt following the catastrophe. Marine ecosystems suffered devastating losses. Ammonites, shelled cephalopods that had flourished for hundreds of millions of years, went extinct completely. Marine reptiles, including mosasaurs and plesiosaurs, disappeared. Many fish groups were decimated. Yet some marine life survived, including sharks, rays, and various fish families. These survivors shared traits that may have helped them persist: ability to tolerate environmental fluctuations, generalist diets, and in some cases the capacity to survive in deep water, where conditions remain more stable than at the surface. Antarctica's recovery from the extinction was slow and complex. Early Paleocene fossil deposits show impoverished ecosystems with low diversity compared to late Cretaceous assemblages. Fern-dominated vegetation gradually gave way to mixed forests as surviving plant lineages expanded and filled empty niches. Conifers, including araucarians and podocarps, returned, though their diversity was reduced. Southern beaches, nothofagus, became increasingly important, eventually dominating many Antarctic forests. These trees were well adapted to cool, temperate conditions and could tolerate the seasonal light variations of high latitudes. Flowering plants recovered and diversified, with new families appearing alongside Cretaceous survivors. Fossil pollen shows gradual increases in diversity through the Paleocene, though it took millions of years for plant communities to approach the complexity of pre-extinction forests. Some plant families that had been minor components of Cretaceous floras became dominant in the Paleocene, taking advantage of opportunities created by the extinction of competitors. This ecological reorganization reshaped Antarctica's vegetation in ways that would persist through the remainder of the Cenozoic. Mammals began their radiation into the ecological spaces vacated by dinosaurs, though in Antarctica this process was somewhat delayed compared to other continents. Early Paleocene mammal fossils from Antarctica are rare, possibly due to poor preservation or simply to low population densities in recovering ecosystems. What fossils exist suggest small-bodied mammals, probably insectivores and omnivores, exploring newly available niches. These mammals faced unique challenges in Antarctic environments: the extreme photoperiod, seasonal food availability, and climate that, while warmer than today, was cooling from Cretaceous highs. Birds diversified rapidly in the Paleocene, with new families appearing that would eventually give rise to modern bird groups. In Antarctica, birds filled roles as seed predators, insect hunters, and small, vertebrate predators. Some evolved flightlessness, becoming ground-dwelling herbivores or predators in ecosystems where mammalian competition was limited. These flightless birds would become increasingly important components of Antarctic fauna in later periods, eventually producing giants that dominated the landscape. The extinction boundary marks a fundamental shift in Earth's biological history and in Antarctica's trajectory. The continent that had hosted dinosaurs for over 100 million years would never see their return. Instead, new players, mammals and birds descended from extinction survivors, would reshape Antarctic ecosystems. Yet for several million years after the extinction, Antarctica remained warm and vegetated, continuing to support diverse life, even as the composition of that life transformed. The freeze was still far in the future. First would come a golden age of mammals and birds, a final burst of abundance before the cooling began. Paleocene mammals and forests. The Paleocene epoch represents a period of recovery and reorganization in Antarctica, as ecosystems rebuilt following the end Cretaceous extinction. Though global temperatures had dropped from their Cretaceous peaks, Antarctica remained warm and forested, with climates comparable to modern temperate rainforests of New Zealand or southern Chile. Sea levels remained high, creating extensive coastal lowlands and shallow seas that moderated temperatures through heat exchange. The interior of the continent was elevated but not yet uplifted to the extreme heights that modern Antarctica reaches. The transantarctic mountains were lower, allowing moisture to penetrate farther inland and supporting vegetation across broader areas than late in the Cretaceous. Forests dominated the Antarctic landscape, but their composition had shifted from Cretaceous patterns. Southern beaches, Nothofagus, became the primary canopy trees, forming dense forests that dropped leaves seasonally in response to winter darkness rather than cold. Fossil leaves show a variety of Nothofagus species, from large-leafed forms suggesting warm, wet conditions to smaller leaf species indicating cooler or drier habitats. The diversity of leaf shapes and sizes reveals that Antarctic forests were complex, with different plant communities occupying different elevations, aspects, and drainage patterns across the landscape. Podocarps, southern hemisphere conifers, remained important forest components, particularly in wetter areas and at higher elevations. These trees produced fleshy cones that were likely dispersed by birds and possibly mammals, creating mutualisms that shape both plant and animal evolution. Araucarian conifers, which had been dominant in the Cretaceous, declined in importance but didn't disappear, persisting in scattered populations and possibly restricted to particular soil types or elevations. Fossil wood from all three groups shows growth rings indicating seasonal growth patterns, with wide rings during productive summer months and narrow or absent rings during winter dormancy. Understory vegetation included a rich array of ferns, club mosses, and flowering plants. Fossil assemblages show fern diversity remained high, with dozens of species adapted to different light levels and moisture conditions. Some grew in deep forest shade, their large fronds maximizing light capture in dim conditions. Others colonized forest gaps created by fallen trees or other disturbances, their spores dispersing widely and establishing populations quickly. Flowering plants diversified into shrubs, herbs, and climbers, filling niches that would have been occupied by similar growth forms in modern temperate forests. Mammals were diversifying but remained relatively small throughout the Paleocene. Fragmentary fossils suggest the presence of primitive marsupials related to those that would later dominate Australia and South America. These early marsupials were probably omnivorous, eating insects, small vertebrates, and plant material depending on seasonal availability. Their fossils indicate active lifestyles. Limb bones show adaptations for climbing and running, suggesting they forage both on the ground and in trees. Dental features reveal varied diets, with some species showing sharp-cusped teeth for eating insects, while others had more generalized dentition capable of processing mixed diets. Birds continued their post-extinction radiation, with Paleocene deposits showing increased diversity compared to immediately after the extinction. Fossil evidence is sparse but suggestive. Isolated bones show the presence of various flying and possibly flightless forms. Some birds were becoming specialized for aquatic lifestyles, with adaptations for swimming and diving to catch fish. These early aquatic birds were ancestors of groups that would later produce penguins and other swimming birds that became characteristic of Antarctica's coastal environments. The transition from flying to swimming lifestyles in Antarctic birds may have been driven by abundant marine resources and limited terrestrial predators. In water, birds faced competition from fish and marine reptiles, but those competitors were reduced by the end Cretaceous extinction. The aquatic realm offered opportunities for birds that could evolve appropriate swimming and diving adaptations. Over millions of years, some lineages would perfect these adaptations, eventually losing flight entirely and becoming specialized pursuit divers. Freshwater ecosystems supported diverse communities of fish, amphibians, and aquatic invertebrates. Rivers flowing from interior highlands carried sediment and nutrients to coastal regions. creating deltas and estuaries that were among the most productive habitats. Fossil deposits in these areas show abundant plant remains, insect fossils, and evidence of fish populations. The fish included lungfish, which survived the extinction and continued in Antarctic freshwater systems, and various ray-finned fish that were diversifying into new niches in the absence of competition from extinct Cretaceous forms. Invertebrates were abundant and diverse, though their fossil record is limited. Insect fossils show the presence of beetles, flies, and possibly early ants, or bees. These insects were crucial components of ecosystem functioning, serving as pollinators, decomposers, and prey for vertebrates. Wood-boring beetles left distinctive tunnels in fossil logs, showing that decomposition of dead trees was an active process. Leaf-mining insects created characteristic feeding traces in fossil leaves, revealing that herbivorous insects had adapted to Antarctic plant communities. Climate during the Paleocene was generally stable, though cooler than the Cretaceous. Temperature reconstructions based on fossil plants and isotope ratios suggest mean annual temperatures in the range of 10 to 15 degrees Celsius, comparable to modern temperate zones. Seasonality was moderate, with winters cool, but not freezing, and summers warm. Precipitation was abundant year-round, though possibly with seasonal maxima during warmer months when evaporation from oceans was highest. This climate supported year-round liquid water in most areas, maintaining rivers, lakes, and coastal wetlands. Ocean circulation during the Paleocene brought relatively warm water to Antarctica's coasts, maintaining temperatures that prevented sea ice formation even during winter months. The currents delivered nutrients that supported productive marine ecosystems around the continent's margins. These productive waters would have been crucial for the evolution of aquatic birds and marine mammals that were beginning to explore ocean resources. The lack of a circumpolar current, which would later isolate Antarctica thermally, meant warm tropical waters could reach high latitudes, fundamentally altering the climate and ecology compared to modern patterns. Volcanic activity continued intermittently, particularly along the Antarctic Peninsula and Marie birdland. Eruptions deposited ash layers that show up in sediment cores, providing time markers for correlating rock units across different regions. These volcanic episodes could have local environmental impacts, disrupting ecosystems temporarily, but also provided benefits through nutrient additions as ash weathered. The volcanism was related to ongoing plate tectonic activity as Gondwana's fragmentation continued and new ocean basins opened. By the late Paleocene, conditions were set for the warming event that would mark the beginning of the Eocene, the Paleocene-Eocene thermal maximum. This dramatic climate perturbation would push Antarctic temperatures to their highest levels of the Cenozoic, creating conditions that supported the most diverse and productive ecosystems the continent would ever experience before the onset of glaciation. The golden age of Antarctic life was about to begin. The Paleocene-Eocene thermal maximum. Approximately 56 million years ago, Earth's climate underwent one of the most dramatic warming events in the Cenozoic, the Paleocene-Eocene thermal maximum, PETM. Over just a few thousand years, global temperatures rose by 5 to 8 degrees Celsius, driven by massive releases of carbon into the atmosphere and oceans. The source of this carbon remains debated. Possibilities include volcanic eruptions, methane released from seafloor sediments, or burning of organic material. But the effects were clear and global. Antarctica, already warm and forested, became even warmer, transforming into a near-tropical environment where palm trees, crocodilians, and mammals adapted to heat dominated the landscape. The evidence for this warming in Antarctica comes from multiple sources. Fossil plants from PETM-age deposits include forms that today live only in subtropical or tropical climates. Most dramatically, fossils of palm-like plants have been found in Antarctic sediments from this period, indicating that winter temperatures remained above freezing. Palms cannot tolerate hard freezes, and their presence demonstrates that Antarctic winters were mild. Fossil wood shows reduced or absent growth rings, suggesting year-round growing seasons without the pronounced dormancy typical of earlier periods. This pattern indicates that even during the dark polar winter, temperatures remained high enough for at least minimal plant growth. Pollen assemblages from PETM deposits show a dramatic spike in diversity, with many new plant families appearing suddenly in the fossil record. This diversification was likely driven by both migration of tropical plants into polar regions as temperature gradients weakened and by evolution of new forms in response to unique Antarctic conditions. The combination of high temperatures and extreme photoperiod, continuous summer sun for months followed by winter darkness, created an environment unlike anywhere on modern Earth, potentially driving evolution of novel adaptations. Animal life responded dramatically to the PETM warming. Mammals diversified rapidly, with body sizes generally decreasing, a common response to warming temperatures that reduces heat retention. Fossil teeth and jaw fragments show the appearance of new mammal groups in Antarctica, including possible early primates or primate relatives. These mammals were adapted to warm, forested environments and likely spent significant time in trees foraging for fruits, insects, and leaves. Their presence in Antarctica confirms that primate-like mammals achieved wide distribution early in their evolutionary history, reaching even the highest latitudes when climate permitted. Reptiles expanded their ranges dramatically during the PETM. Crocodilians, which had been present in Antarctica during warmer Mesozoic periods but were absent or rare in the Paleocene, returned as temperatures rose. Crocodilian fossils from PETM deposits show they reach considerable sizes, indicating stable populations with access to abundant prey. Modern crocodilians are ectothermic, depending on environmental temperatures for body heat, and their presence in PETM Antarctica confirms that even winter temperatures remained within their thermal tolerance range, at least 7 to 10 degrees Celsius. Birds underwent significant changes during the PETM. Some lineages that had been evolving toward aquatic lifestyles accelerated their adaptations, with increasing specialization for diving and swimming. Fossil bones show progressive modifications, wings becoming more flipper-like, legs shifting backward on the body for better propulsion, and bones becoming denser to reduce buoyancy. These changes would culminate in the full penguins that would appear in the early Eocene. But during the PETM, they were intermediate forms testing various aquatic adaptations. Terrestrial bird diversity increased as well, with new families appearing that exploited the productive forest environments. Fossil evidence suggests the presence of early relatives of modern songbirds, parrots, and other groups that would later diversify extensively. The abundance of insects and fruits in PETM forests provided ample resources for these birds, supporting communities comparable in diversity to modern tropical rainforests. Marine ecosystems around Antarctica experienced profound changes. Ocean temperatures rose several degrees, and the increased temperature differential between surface and deep waters may have enhanced stratification, reducing nutrient upwelling in some areas while intensifying it in others. Plankton communities shifted toward warm water species, changing the base of marine food webs. These changes propagated upward through the ecosystem, affecting fish populations, marine mammals, and seabirds that depended on ocean productivity. The ocean acidification that accompanied the PETM, caused by absorption of atmospheric carbon dioxide, stressed calcifying organisms, including shellfish and plankton, with calcium carbonate skeletons. Fossil records show extinction of some deep-sea foraminifera and reduction in carbonate sediment accumulation, indicating that ocean chemistry changes were significant. Yet many organisms adapted or shifted distributions, and overall marine diversity remained high. Weathering rates increased dramatically during the PETM as higher temperatures and increased rainfall accelerated chemical breakdown of rocks. This weathering consumed atmospheric carbon dioxide over time, eventually drawing down carbon levels and leading to gradual cooling. Rivers carried increased sediment and nutrient loads to oceans, potentially fertilizing coastal waters and enhancing productivity. Fossil soils from this period show evidence of intense tropical-style weathering, with deeply leached profiles indicating heavy rainfall and rapid breakdown of parent rock. The duration of the PETM was geologically brief, perhaps 100 to 200,000 years, but its impacts were profound and lasting. As carbon gradually cycled out of the atmosphere through weathering and ocean uptake, temperatures slowly declined from their peak. By the Middle Eocene, conditions had cooled somewhat, but remained much warmer than the pre-PETM Paleocene. Antarctica would stay warm and forested for millions of years more, but the peak warmth of the PETM represented the absolute climax of Antarctic biodiversity in the Cenozoic. The PETM also left a permanent mark on Antarctica's biota. Many of the mammal, bird and plant lineages that appeared or diversified during this event would persist through subsequent cooler periods, adapting as conditions changed. The genetic and ecological innovations that allowed survival in PETM Antarctica, tolerance of seasonal darkness combined with high temperatures, ability to exploit abundant resources during brief productive seasons, and flexibility in response to rapid environmental change would prove valuable as the climate began its long descent toward glaciation. For Antarctica, the PETM was simultaneously a peak and a turning point. Never again would the continent experience such warmth and productivity. The subsequent Eocene would see gradual cooling begin, setting the stage for the transformation that would ultimately bury the forests under ice and reduce the once rich ecosystems to a few scattered survivors clinging to ice-free patches. But for a brief moment in geologic time, Antarctica basked in near-tropical warmth, hosting ecosystems as diverse and productive as any on Earth. Eocene diversity peak. The Eocene epoch, spanning from about 56 to 34 million years ago, represents the last great age of abundant life in Antarctica before the onset of glaciation. Following the extreme warmth of the Paleocene-Eocene thermal maximum, temperatures remained elevated though gradually cooling through the epoch. Antarctica continued to be covered by extensive forests and supported diverse communities of mammals, birds, reptiles, and plants. This was the final period when Antarctica functioned as a truly habitable continent, connected to South America via land bridges and serving as a corridor for biological exchanges between southern continents. Eocene forests in Antarctica were dominated by southern beeches, Nothofagus, which formed the primary canopy in most regions. Fossil leaves from these forests show remarkable diversity in size and shape, indicating multiple species occupying different ecological niches. Some Nothofagus species had large, broad leaves suggesting warm, moist conditions similar to modern temperate rainforests. Others had smaller, more leathery leaves indicating adaptation to drier or more exposed habitats, such as hillsides or areas with sandy soils. The abundance of Nothofagus fossils in Antarctic rocks demonstrates these trees were superbly adapted to high-latitude conditions, tolerating the extreme photoperiod while thriving in the relatively warm climate. Flowering plants diversified extensively during the Eocene, filling understory and edge habitats with shrubs, herbs, and climbing vines. Fossil flowers and fruits show the presence of many families still found in modern southern hemisphere floras, including Proteaceae, Myrtaceae, and various other groups characteristic of temperate rainforests. These plants developed mutualisms with animal pollinators and seed dispersers, creating ecological networks that increased overall biodiversity. The fossil record shows abundant insect-damaged leaves, indicating that herbivorous insects were diverse and had evolved specialized feeding preferences for particular plant groups. Mammals reached their greatest diversity in Antarctica during the early and middle Eocene. Marsupials were particularly successful, with fossils showing multiple lineages, including early relatives of Australian possums and South American marsupials. These marsupials ranged in size from mouse-like insectivores to larger omnivores, possibly the size of raccoons. Their dental features reveal varied diets. Some had sharp cusped teeth for eating insects. Others had broader molars for grinding plant material and tough foods. Limb bones show adaptations for climbing, indicating that many species were arboreal, living in the forest canopy, where they fed on fruits, insects, and possibly bird eggs. Birds underwent dramatic evolution during the Eocene, with multiple lineages becoming highly specialized for marine lifestyles. The most famous Antarctic birds of this period were early penguins, which had evolved from flying ancestors into powerful swimmers. Eocene penguin fossils show they were already highly adapted for pursuit diving. Streamlined bodies, wings modified into flippers, and legs positioned far back for underwater propulsion. However, Eocene penguins were much larger than most modern species, with some reaching heights of over 1.5 meters and possibly weighing 40 kilograms or more. These giant penguins were formidable predators, capable of diving to considerable depths to catch fish and squid. The evolution of penguins in Antarctica was driven by abundant marine resources and relatively few competitors. During the Eocene, seals and other marine mammals had not yet arrived in Antarctic waters, leaving fish-eating niches open for exploitation by birds. Penguins filled these niches efficiently, evolving into multiple species with different feeding strategies. Some were pursuit divers, chasing fast-moving fish in open water. Others may have been benthic feeders, diving to the seafloor to catch bottom-dwelling fish and invertebrates. This ecological diversity allowed multiple penguin species to coexist without directly competing. Flying birds also diversified during the Eocene, with fossils showing the presence of multiple seabird families. Early albatrosses or their relatives developed long, narrow wings for efficient soaring over oceans, taking advantage of Antarctic wind patterns to travel vast distances in search of food. Petrels and shearwaters exploited different feeding niches, using their acute sense of smell to locate prey or scavenging opportunities. Coastal areas supported wading birds and shorebirds that fed on intertidal invertebrates, exposed during low tides. Terrestrial birds included early relatives of modern songbirds, parrots, and possibly ratites, the group including modern ostriches and emus. Some Antarctic birds during the Eocene may have been flightless, adapting to terrestrial lifestyles in the absence of large mammalian predators. These flightless forms would have filled ecological roles as seed predators, herbivores, or small prey hunters, occupying niches that on other continents were dominated by mammals. Reptiles remained components of Eocene Antarctic fauna, though their diversity was declining as temperatures cooled through the epoch. Crocodilians persisted in freshwater environments during the early Eocene, but may have disappeared from Antarctica by the middle to late Eocene as conditions became marginal for their survival. Their presence in early Eocene deposits confirms temperatures remained relatively warm early in the epoch, but their absence from later deposits indicates cooling was affecting even cold-tolerant species. Ocean circulation patterns during the Eocene were fundamentally different from today. The Drake Passage between South America and Antarctica had not yet fully opened, preventing establishment of a circumpolar current. Instead, ocean currents could penetrate to high latitudes, bringing relatively warm water from tropical and subtropical regions. This pattern maintained moderate ocean temperatures around Antarctica's coasts, supporting productive marine ecosystems and preventing sea ice formation even during winter months. Marine productivity around Antarctica was high, driven by nutrient inputs from rivers and by upwelling currents that brought deep, nutrient-rich water to the surface. These productive waters supported abundant plankton populations, which in turn fed fish, squid, and other invertebrates. Marine mammals had not yet colonized Antarctic waters in significant numbers, leaving fish-eating niches available for birds, particularly penguins, which exploited these resources extensively. Volcanic activity continued along the Antarctic Peninsula and in Marie Byrd Land, related to subduction along the Pacific margin of Gondwana. Eruptions deposited ash layers that show up in sediment cores, providing valuable time markers for dating rock sequences. These volcanic episodes had local environmental impacts, with ashfalls potentially devastating nearby ecosystems temporarily. However, the volcanic activity also created new land through lava flows and built mountains that influenced weather patterns and created habitat diversity. By the late Eocene, the first signs of cooling were becoming apparent in the fossil record. Plant assemblages began showing increased proportions of cold-tolerant species and decreased diversity of warm-adapted forms. Tree growth rings became more pronounced, indicating greater seasonality in temperature or precipitation. These changes were subtle but consistent, showing that the climate was shifting toward the cooler conditions that would characterize the Oligocene. The golden age of Antarctic life was approaching its end, though several million years would pass before glaciation truly transformed the continent. The opening of Drake Passage. The separation of South America from Antarctica and the subsequent opening of Drake Passage represents one of the most consequential tectonic events in Cenozoic climate history. This opening allowed the establishment of the Antarctic Circumpolar Current, fundamentally altering ocean circulation patterns and initiating Antarctica's transformation from a forested continent to an ice-covered desert. The exact timing of Drake Passage opening remains debated, with estimates ranging from about 41 to 23 million years ago. But the consensus places initial opening around the Eocene-Oligocene boundary approximately 34 million years ago, with full oceanic circulation established several million years later. Prior to this opening, Antarctica and South America were connected by a land bridge or narrow seaway that restricted deep water flow between the Pacific and Atlantic Oceans. Ocean currents from tropical regions could penetrate to high southern latitudes, delivering warm water that moderated Antarctic temperatures. This pattern maintained relatively warm conditions despite Antarctica's polar position. The landmass connection also allowed free movement of terrestrial organisms between the continents, maintaining genetic exchange and preventing isolation of Antarctic populations. The rifting process that led to Drake Passage opening was gradual, driven by motion of tectonic plates as South America moved northward and Antarctica remained relatively stationary. Volcanic activity and earthquake activity increased along the future passage route as continental crust thinned and eventually fractured. Fossil evidence suggests that intermittent shallow seaways may have existed earlier, allowing occasional marine exchanges but not full ocean circulation. These early seaways would have flooded during high sea level stands and closed during low stands, creating variable conditions over millions of years. As the passage widened, ocean circulation patterns began changing. Initially, the opening may have been too shallow or narrow to allow deep water passage, restricting flow to surface currents only. But as rifting continued, the passage deepened and widened sufficiently to allow establishment of a circumpolar current, a west to east flowing current that circled Antarctica without interruption. This isolated Antarctica from warm water inputs, trapping cold water around the continent and setting the stage for glaciation. The timing of glaciation onset at the Eocene-Oligocene boundary correlates closely with Drake Passage opening, suggesting a causal relationship. Once the circumpolar current was established, Antarctic coastal waters cooled several degrees. This cooling affected atmospheric temperatures as well, since oceans and atmosphere exchange heat continuously. As temperatures dropped, precipitation that fell as rain during the Eocene began falling as snow at higher elevations. This snow persisted through summer months rather than melting completely, beginning the accumulation that would eventually form ice sheets. The environmental impacts in Antarctica were severe and relatively rapid in geologic terms. Forests that had covered the continent for millions of years began dying as temperatures fell below tolerances. Cold-sensitive plant species disappeared first, leaving communities dominated by increasingly cold-adapted forms. Nothofagus persisted longer than other groups, showing its superior adaptation to Antarctic conditions. But even these hardy trees eventually retreated to coastal areas and lower elevations as the interior highlands became too cold. Animal communities experienced dramatic disruption as the forest declined. Mammals that had diversified through the Eocene faced shrinking habitats and declining food resources. Herbivorous mammals suffered as plant productivity decreased. Carnivores and omnivores that depended on diverse prey communities found their food sources diminishing. Many lineages went extinct in Antarctica, surviving only in South America or Australia, where conditions remained more favourable. Some mammals may have migrated across the narrowing land bridge to South America before it fully submerged, escaping the deteriorating Antarctic climate. Birds fared somewhat better, particularly those adapted to marine environments. Penguins continued thriving as ocean productivity remained high despite cooling waters. In fact, cooling may have enhanced productivity by strengthening upwelling currents. These aquatic birds were less dependent on terrestrial ecosystems and could migrate to ice-free coastal areas where they nested and raised young. Flying seabirds similarly maintained populations by exploiting marine resources, their mobility allowing them to range widely in search of food. The fossil record shows a marked decline in diversity at the Eocene-Oligocene boundary. Pollen assemblages from this transition show dramatic decreases in angiosperm diversity and increases in cold-tolerant conifers and ferns. Mammal fossils become rare to absent in rocks younger than this boundary, indicating most mammal lineages disappeared from Antarctica. Insect diversity likely declined as well, though direct evidence is limited. The complex multi-layered ecosystems that had characterized Eocene Antarctica were simplifying rapidly as harsh conditions eliminated species unable to adapt. Yet some life persisted. Nothofagus forests continued in sheltered coastal areas and valleys that retained relatively mild microclimates. These forests supported reduced but functioning ecosystems, including invertebrates, birds, and possibly some small mammals through the early Oligocene. Cold-adapted plants including mosses, liverworts, and hardy ferns colonized areas where forests had died, creating tundra-like communities. These plants were adapted to short growing seasons, low temperatures, and the extreme photoperiod that remained a defining feature of Antarctic environments. Marine ecosystems underwent reorganization rather than collapse. The cooling waters and establishment of the circumpolar current created productive conditions that supported abundant fish populations. Penguins diversified into multiple species adapted to different depths and prey types. Early seals appeared in Antarctic waters for the first time, beginning their evolution into specialized marine hunters. These marine mammals had evolved from terrestrial ancestors and were adapting to fully aquatic lifestyles, exploiting fish and invertebrate populations around Antarctica's coasts. The circumpolar current itself became a defining feature of the Southern Ocean, creating conditions that would persist to the present day. The current isolated Antarctica not just thermally, but also biologically, restricting dispersal of organisms between Antarctica and other continents. This isolation would drive unique evolutionary patterns in Antarctic marine life, with species evolving distinctive adaptations to cold water conditions without gene flow from lower latitudes. Fish evolved antifreeze proteins allowing survival in water at temperatures below the normal freezing point. Invertebrates developed cold adaptations and grew to unusually large sizes, gigantism driven by high oxygen solubility in cold water. The opening of Drake Passage marked the beginning of the end for Antarctica as a living continent. While life would persist in increasingly restricted refugia for millions of years more, the trajectory was set toward the ice-covered conditions that dominate today. The productive forests and diverse animal communities that had flourished for hundreds of millions of years were entering their final chapter, to be replaced by ice sheets kilometers thick and ecosystems restricted to the narrow margins where ice and ocean meet. Oligocene tundra. The Oligocene epoch, spanning from about 34 to 23 million years ago, saw Antarctica's transformation accelerate as temperatures continued declining and ice began accumulating at scale. This was the period when Antarctica shifted from a forested continent to one dominated by tundra and eventually by ice sheets. The transformation was neither uniform nor linear. Warmer intervals temporarily reversed cooling trends, allowing forests to briefly expand again before the next cooling pulse drove them back. But the overall trajectory was clear. Antarctica was freezing, and life was retreating to the coasts and to ice-free pockets where conditions remained marginally habitable. Early Oligocene deposits show the persistence of nothofagus forests in coastal areas, particularly along the Antarctic Peninsula and in coastal valleys of East Antarctica. These forests were simplified compared to Eocene assemblages, fewer species, less structural complexity, and more limited extent. Fossil leaves show that nothofagus species present during this period were cold-adapted forms, with small, leathery leaves resistant to freezing damage. Growth rings in fossil wood became extremely pronounced, showing short, intense growing seasons followed by long, dormant periods. Some fossil trees show growth rings indicating they survived for decades or even centuries, suggesting that successful establishment was difficult, but that individuals could persist once established. As the Oligocene progressed, tundra ecosystems expanded at the expense of forests. Tundra vegetation consisted of low-growing plants, dwarf shrubs, grasses, sedges, and herbaceous flowering plants, adapted to cold temperatures, strong winds, and short growing seasons. These plants survived by growing close to the ground, where a boundary layer of still air provided slight insulation from wind chill. Many developed cushion or mat growth forms, maximizing heat retention and minimizing exposure. Fossil pollen from Oligocene deposits shows increasing proportions of grass and sedge pollen relative to tree pollen, documenting this vegetation transition. Mammal diversity in Antarctica declined severely during the Oligocene. The fossil record from this period contains few mammal remains, suggesting most lineages went extinct as habitats deteriorated. Any mammals that persisted would have been small-bodied forms capable of surviving on limited food resources. They might have included insectivores feeding on the invertebrate populations that persisted in tundra and coastal habitats, or small omnivores with flexible diets. However, direct evidence for Oligocene mammals in Antarctica is essentially absent, indicating they were at best rare and at worst completely extinct on the continent. Birds adapted more successfully to Oligocene conditions. Penguins continued diversifying, with multiple species exploiting Antarctic marine resources. Some penguin fossils from this period show extremely large body sizes, species taller than modern emperor penguins and possibly weighing 50 kilograms or more. These giants were apex predators in coastal ecosystems, diving deep to catch fish and squid. The absence of competition from marine mammals, which had not yet diversified extensively in Antarctic waters, allowed these giant penguins to dominate their niches. Flying seabirds maintained populations around Antarctica's coasts, nesting on ice-free areas and ranging widely over oceans in search of food. The increased ocean productivity, driven by cooling waters and strong upwelling currents, provided abundant resources. Albatrosses Petrels and other seabirds evolved increasingly refined flight adaptations, allowing them to exploit wind patterns efficiently and travel vast distances with minimal energy expenditure. These birds became true ocean wanderers, spending most of their lives at sea and returning to land only to breed. Invertebrate populations declined along with vegetation. Insects that depended on flowering plants for food or pollination services disappeared as those plants went extinct. Cold-adapted insects, including some flies and springtails, persisted. Their life cycles adapted to short summers and long winters. Many invertebrates developed antifreeze compounds in their body fluids, allowing survival at temperatures well below freezing. Others survived by entering diapause, a state of suspended development during unfavorable seasons. Marine ecosystems continued functioning relatively normally despite atmospheric and terrestrial cooling. The oceans cooled as well, but marine organisms adapted more successfully than terrestrial forms. Fish populations remained abundant, supporting penguins, seals, and seabirds. The first true Antarctic seals appeared during the Oligocene, early members of lineages that would diversify extensively in later periods. These seals evolved from terrestrial carnivore ancestors, probably entering the ocean in temperate regions, before dispersing to Antarctic waters, where abundant fish populations provided ample food. Ice sheets began forming in East Antarctica during the Oligocene, first in highlands, where snow accumulated faster than it melted. These ice caps expanded gradually, flowing outward under their own weight and scouring valleys as they moved. The advance of ice eliminated ecosystems in affected areas, burying vegetation and soil under permanent ice. Only areas at the margins, ice-free coasts and valleys where glaciers hadn't yet advanced, retained life. The expansion of ice had profound effects beyond simply covering the landscape. Ice sheets reflected sunlight efficiently, reducing heat absorption and creating a positive feedback that accelerated cooling. The growing ice also locked up water, lowering global sea levels and exposing continental shelves. Around Antarctica, this sea level drop created broader coastal plains that briefly expanded terrestrial habitat before ice advanced to bury them. Climate modelling suggests Oligocene Antarctica experienced extreme seasonal temperature variations. Summer temperatures in ice-free areas might have reached 5 to 10 degrees Celsius, allowing brief periods of plant growth and biological activity. Winter temperatures plunged well below freezing, with coastal areas experiencing temperatures similar to modern sub-Antarctic islands. Interior regions under developing ice sheets were even colder, with temperatures approaching modern Antarctic conditions. Despite the harsh conditions, life persisted through most of the Oligocene in scattered refugia. The Antarctic Peninsula, which extends northward towards South America, remained relatively mild and retained more vegetation than interior regions. Coastal valleys with favourable exposure and protection from wind maintained tundra communities longer than exposed areas. These refugia served as reservoirs of biodiversity, allowing some species to survive that would otherwise have gone extinct. By the late Oligocene, Antarctica was predominantly ice-covered, with only scattered ice-free areas around coasts and in a few interior mountain ranges. The continent's transformation from the forested, diverse ecosystem of the Eocene to an ice-dominated landscape was nearly complete. One final transition remained. The Miocene would see further cooling and ice sheet expansion, reducing ice-free areas to the tiny scattered pockets that exist today. The age of abundant Antarctic life was over. The age of ice had begun. Pliocene-Pleistocene, final freeze. The Pliocene and Pleistocene epochs, spanning from about 5 million years ago to the present, saw Antarctica reach its current state of near-complete glaciation. While the Miocene had established extensive ice sheets, these final epochs saw ice coverage become permanent and nearly total, with only about 1% of Antarctica remaining ice-free today. This final freeze was driven by continued cooling of global climate, with multiple ice age cycles creating periods of even more extensive glaciation alternating with slightly warmer interglacials, when ice sheets retreated marginally. Through all these fluctuations, Antarctica remained frozen, its ice sheets serving as the stable foundation upon which Northern Hemisphere ice sheets waxed and waned. During the Pliocene, between 5 and 2.5 million years ago, global temperatures were slightly warmer than today, and Antarctica may have experienced some ice sheet retreat compared to the present. Geological evidence suggests the West Antarctic ice sheet, which rests on bedrock below sea level, may have been smaller or even absent during warm intervals of the Pliocene. This would have allowed marine waters to penetrate farther into West Antarctica, creating seaways where ice currently exists. However, the East Antarctic ice sheet, larger and resting primarily on bedrock above sea level, remained relatively stable, maintaining permanent ice cover over most of East Antarctica throughout the Pliocene. Terrestrial life during the Pliocene was restricted to the same types of habitats that support life today: ice-free coastal areas, nunataks, mountain peaks protruding through ice sheets, and the rare ice-free valleys where local conditions prevent glacier formation. These environments supported simple ecosystems dominated by mosses, lichens, and invertebrates. No vascular plants, flowering plants or ferns survived in Antarctica by this time, having been eliminated during earlier cooling. The vegetation that remained consisted entirely of cryptogams, plants that reproduce by spores rather than seeds. Invertebrate life persisted in these ice-free areas adapted to extreme conditions. Springtails, columbola, and mites, acari, are the dominant terrestrial arthropods, existing in populations that fluctuate with microclimate conditions. These tiny organisms feed on microbes, fungi, and organic detritus, forming simple food webs. Their life cycles are adapted to short summers, rapid development when conditions allow, followed by overwintering in protected microhabitats. Some Antarctic invertebrates can survive being frozen solid, their body fluids containing antifreeze proteins and cryoprotective compounds that prevent lethal ice crystal formation in cells. During the Pleistocene, beginning about 2.5 million years ago, Earth entered a period of cyclical glaciations, ice ages, driven by variations in Earth's orbit and axial tilt. These Milankovitch cycles created alternating cold periods when ice sheets expanded globally and warmer interglacial periods when ice retreated. While these cycles dramatically affected ice coverage in the Northern Hemisphere, Antarctica remained relatively stable. Its ice sheets were already at or near maximum extent, and even during warm interglacials, they retreated only marginally. Ice core records from Antarctica, extracted by drilling deep into ice sheets, provide detailed climate records covering the past 800,000 years. These cores contain ice formed from accumulated snowfall, with each layer preserving atmospheric gases, dust, and isotopic signatures that reveal temperature and atmospheric composition at the time of formation. Analysis of these cores shows that Antarctic temperatures fluctuated by about 10 degrees Celsius between cold glacial periods and warm interglacials, but these fluctuations occurred around average temperatures well below freezing. Antarctica never warmed sufficiently during interglacials to allow significant ice sheet melting or vegetation re-establishment. Marine ecosystems around Antarctica continued thriving through the Pleistocene, adapted to cold conditions. Penguin populations fluctuated with ice extent. During glacial maxima, when sea ice extended farther from the continent, penguin colonies shifted northward or concentrated at ice edges where access to ocean waters remained possible. During interglacials, they could establish colonies closer to the continent as nearshore waters became ice-free seasonally. Different penguin species showed different tolerances for ice conditions, with some preferring areas with fast ice for nesting, while others required ice-free rocky coasts. The approach of modern times saw minimal change in Antarctic conditions. The continent remained frozen through the warm intervals of the Holocene, the current interglacial period that began about 12,000 years ago. While northern hemisphere ice sheets melted and sea levels rose dramatically, Antarctica's ice sheets remained stable, losing only marginal ice from coastal areas. The flora and fauna present in Antarctica today, mosses, lichens, springtails, mites, nematodes, penguins, seals, and seasonal whales, are the descendants of lineages that survived through multiple glacial-interglacial cycles, their adaptations to extreme cold, allowing persistence where almost all other life was eliminated. Antarctica's transformation from the lush forests of the Eocene to the ice desert of today represents one of the most dramatic environmental changes in Earth history. The continent that once hosted dinosaurs, palm trees, and diverse mammals became a frozen wasteland where only the hardiest life persists. Yet hidden within the ice and in the fossil record preserved in rocks around the continent's margins lies evidence of that lost world. Fossil leaves from tropical plants, bones of extinct animals, and pollen from forests that once covered the landscape. These fossils tell the story of Antarctica's past, reminding us that even the most extreme environments on Earth were once radically different, and that planetary climate can change dramatically on timescales that seem long to humans, the last refugia. Even as Antarctica froze and ice sheets expanded to cover nearly the entire continent, small pockets of ice-free land persisted as refugia where life could continue. These refugia, scattered along coasts, in isolated mountain valleys, and on nunataks jutting above the ice, became the final strongholds of terrestrial life in Antarctica, supporting simplified but functioning ecosystems that continue to the present day. Understanding these refugia is crucial for reconstructing how life responded to glaciation and for identifying which organisms successfully adapted to the most extreme terrestrial environments on Earth. The McMurdo Dry Valleys in East Antarctica represent the largest ice-free area on the continent, covering about 4,500 square kilometres. These valleys remain ice-free due to a combination of factors: extremely low precipitation, less than 100 millimetres per year, most falling as snow, strong katabatic winds that sublimate any snow that falls before it can accumulate, and topographic blocking by surrounding mountains that prevents glacier advance. The result is a polar desert more extreme than the Sahara, where liquid water is scarce and temperatures almost never exceed freezing even during summer. Despite these harsh conditions, the dry valleys support life. Endolithic microorganisms, bacteria, algae, and fungi living inside porous rocks obtain moisture from snow that briefly melts on sun-warmed rock surfaces. These organisms grow within the rock matrix, protected from wind and extreme temperature fluctuations. They photosynthesize when sufficient light penetrates the rock, growing slowly but persistently. Stromatolites in ice-covered lakes within the dry valleys show that microbial communities have maintained continuous presence for thousands of years, surviving through multiple climate cycles. Soils in the dry valleys contain nematodes, tardigrades, rotifers, and other microscopic invertebrates that feed on bacteria and fungi. These organisms can survive desiccation and extreme cold by entering cryptobiosis, a state of suspended animation where metabolic activity drops to undetectable levels. When rare moisture events occur, snow melting during exceptionally warm summer days, or fog providing brief humidity, these organisms reactivate, feeding and reproducing rapidly before conditions deteriorate again. Their populations fluctuate dramatically over time, sometimes declining to near extinction before recovering when favourable conditions return. Coastal ice-free areas occur where steep terrain prevents glacier accumulation, or where geothermal heat or dark rock surfaces create localised melting. These areas are small, often just hectares or less, but they support richer life than interior deserts. Mosses and lichens grow more abundantly, where moisture is available from snowmelt or fog. Invertebrate populations are denser and more diverse. Some coastal sites support primitive soil formation with organic matter accumulation creating substrates for colonization by additional organisms. The Antarctic Peninsula, extending north towards South America, hosts the richest terrestrial ecosystems remaining in Antarctica. Its northern regions experience summer temperatures that regularly exceed freezing, allowing more extensive plant growth. Two species of flowering plants, Antarctic hairgrass, Deschampsia antarctica, and Antarctic pearlwort, Colobanthus quitensis, survive on the peninsula, representing the only vascular plants remaining in Antarctica. These plants grow in sheltered locations where soil, moisture, and temperature allow, forming small patches of vegetation that support invertebrate populations. These flowering plants are remarkable survivors, descended from ancestors that colonized Antarctica during warmer periods and persisted through subsequent cooling. They've evolved adaptations including antifreeze proteins, rapid growth during brief favorable periods, and ability to photosynthesize at low temperatures. Their presence demonstrates that vascular plants can survive in extreme polar environments if minimal requirements for soil, moisture, and warmth are met. They represent the trailing edge of Antarctica's plant diversity, the last remnants of flora that once covered the continent. The concept of glacial refugia, areas that remained ice-free during glacial maxima, is crucial for understanding modern Antarctic biodiversity. Genetic studies of moss and lichen populations reveal that many species show genetic structuring consistent with long-term isolation in separate refugia. Different populations accumulated genetic differences while isolated, then expanded and potentially reconnected during warmer periods when ice-free areas grew larger. This pattern of isolation and expansion has shaped the distribution and genetic diversity of Antarctic organisms, creating a complex biogeographic pattern despite the continent's apparent simplicity. The refugia also serve as genetic reservoirs, maintaining biodiversity that could potentially recolonize larger areas if Antarctic climate warms. While current global warming has caused minimal ice retreat in East Antarctica, the Antarctic Peninsula has experienced significant warming with associated glacier retreat and expansion of ice-free areas. Organisms from refugia are colonizing these newly exposed areas, beginning the slow process of ecosystem development on surfaces that haven't seen life for millennia. This colonization provides real-time observations of how ecosystems establish and develop following deglaciation, offering windows into processes that occurred repeatedly through the Pleistocene ice age cycles.